Hello, everybody. Just gonna check before I get started that audio is working correctly. I'm gonna assume it is because I've got things set up well enough now that they're nearly always working correctly. Um, Also, just laughing at the messages at the beginning, treating me like an actual streamer, because one of the messages about liking and subscribing and stuff like that got marked as spam. And that made me laugh. So, um, yeah. So, always funny having those little things happening when we encroach on encroach on the idea of people actually streaming for money and stuff like that. I mean, when it comes down to it, one could say I am technically streaming for money, because I am being paid to be here. Um, but I guess it's slightly different. There's a lot more structure involved. There's a lot more kind of hardcore assessment and stuff like that you're not going to get in a normal live stream. Imagine if a live stream had you've got to watch this live stream for 10 weeks or so. Oops, I just realized I was on my VLabs screen instead of my slides, but that's okay. Oh, I didn't update this. This is very embarrassing. I had that left over from, because these slides are a modification of slides I used last year in a different lecture. But anyway, yeah, so it would be really, really funny if at the end of watching someone stream for 10 weeks, you had to do a massive 24-hour, how much do you actually know about this stream and what's happening in it thing. I mean, that would be quite funny, but I mean, I wouldn't be the first person to stream programming, and I wouldn't be the first person to put up a whole bunch of content online that is very, very professionally useful for someone wanting to be a programmer. So I guess it's not that far-fetched. Oh no, people have devolved again into online ads that are attached to attached to attached to streams. Patrick, I did have an urge, and I'm not going to do it, but I did actually have an urge to live stream during your exam, because us having a take-home open book exam, I mean, who uses books for programming? Open computer exam, because I mean, even our exams, even when they're closed, are run on computers. I did actually have the urge to stream for part of that, but I'm not sure if that's entirely fair, because not everyone in every time zone is going to be able to be there for the stream. So if I go there and I answer some people's questions and not other people's, it's not entirely fair. But part of me was gonna stream for a bit of it, just to hang out and say hi to people and things, which is really interesting, because it takes the idea of an open book exam and makes it less of a you must do this thing, and this kind of high pressure, you have to perform kind of thing. I mean, it still is. It's still something where I want you to take it seriously, and I want you to put your best into it so that you get something out of it, Although exams, I don't think you get as much out of an exam as you get out of the assignments, but at least, you want to show what you're capable of doing after 10 weeks of learning. Yeah, but I think it's very interesting with an open book exam is that I could actually be involved in the exam. Usually in the sit-down exam, when you're there in the labs, I'm there as well. I won't be one of the invigilators walking around in an actual lab, but I'll be supervising the entire set of labs doing the exams. But I think it would be even funnier because it's open book, where we could just talk about it during the exam. Not sure how fair that is. That's something I'd have to think about. We are definitely doing something next week, though. CSE SOC and I think it's Women in Tech, I know it's WIT Society, are getting together to do a study session, and that's going to be in kind of exactly a week's time, next Wednesday afternoon. And because that would usually be us all getting together in a room, chatting and studying and talking about topics and things, we're going to be doing that in some kind of streamed way. So chances are I'll be on live stream like this while a bunch of the CSCSOC experienced coders. I mean, like, a lot of your tutors are actually in CSCSOC as part of the executive and part of the people who work on things. Everyone in CSCSOC has done COMP1511. I'd say roughly half of them have done it under me because I taught it last year. And so there'll be a lot of, like, sort of this last minute help before the exam. The exam, if I remember correctly, is on the first Tuesday of the exam period, so I think it will be just about, I mean, you could roughly say a week and a half after term finishes. I have the exact date written down somewhere. Actually, you probably have the exact date in your calendars already. I think it's already been publicized. If it hasn't, I will look it up and I'll let you know when I send out a notice at the end of the week exactly when the exam is. Don't worry, we're going to cover the exam. I'm going to talk about the exam next week. Things have been shifted around a bit because of the 24-hour open book thing. But one thing I want to do is to give you an exam which is very similar to the exam that I was going to give you if you were going to sit down and had to do it in 3 hours. So you know the weekly tests. The weekly tests, we say, do this in 1 hour. At the end of the hour, you can stop, you can save what you've got in the end of that hour, and just have a decent idea about how you're going in the course. But then you also have all week to do it if you just want to max it out and get 100%. It's not really worth it for the marks, but you can if you want to. That way you can get a measure of feedback of where you're at. The exam we're going to set up in the same way. So we're actually going to set it up like it was a 3-hour exam and give you a chance to do it like that. And so if you want to, you can record everything that you've done at the end of 3 hours and then say, okay, that's how I think I went in the course. But then you can spend the rest of the time for the rest of that day or whatever just trying to max out the marks, which doesn't matter because we are on a pass-fail now, but if you really want to, you can. But those of you who want to do this course in as close as possible a simulation of what it was like when we were assessing it fully, you could, if you wanted to, hand in your exam at the end of 3 hours. If you really want to put yourself in the same kind of pressure cooker that we used to put people in when the exam was in person, you can do that if you want. It might be a bit full on, but considering it's a pass-fail course now, you'll probably still, well, I can't say you're still going to pass, because some people are going to pass, some people are going to fail. But that's inevitable, right? We've got 700 people, so someone is unfortunately going to fail the course. That doesn't mean you can't do computing. That usually just means that right now, the way this is working didn't entirely work for you, and I 100% understand if right now this course isn't working for everyone, because going fully online, I feel, takes away a lot of the support that we would usually give people in our teaching. So I feel like there's a lot of people out there at the moment, whether you're watching or not right now, there's a lot of people out there at the moment that are struggling, and that's totally fine. That's part of what this is, and it's hard to just push through when you're sort of just stuck at home and you're starting to get a bit of cabin fever. You're not getting as much exercise as normal, you're not being as social as normal, maybe, I don't know. I've been having a lot of, like, video chat meetups with friends and stuff, which is weirdly making me more social than normal. Meeting up with more people is very strange. But yeah, so if that's affecting your studies and you feel like things aren't going to go as well as they could have, then don't put any extra pressure on yourself. There's enough pressure coming from the world as it is. No one could have expected, like, 6 months ago that there was going to be a worldwide pandemic that was just going to shut everything down, and everything that you were expecting to do at university was just going to change into something else. So don't worry if this is becoming a really untenable situation. The UNSW has said that if you fail courses in term 1, they don't go on your record. So if that's what happens, and you've got to just kind of write off term 1 and start again in term 2, I don't think that's that big a deal. I don't think that's that big a problem. I think that's like a bump in the road, if anything. and it's not something that's going to genuinely set back your academic career or anything like that. So I wouldn't be too disheartened. I know that this is possibly a way a lot of people are thinking. I wouldn't be too disheartened if things aren't going that well this term. Frankly, things aren't going that well for me this term either, and I think that's because I usually like being out and about. You know, I like meeting up with friends a bit. I like delivering lectures in person. I like to be able to see all your faces as I'm talking to you and things like that. So this has been a little bit different, you know, and I'm sitting here where I usually play games and paint miniatures and stuff, and I'm doing my work here instead. So it's a little bit weird. It's like work has invaded my private spaces, the spaces where I usually take time off work. And I can understand that that's had a psychological effect on me, so it must be having a psychological effect on a lot of you as well. So I'm trying to say that if we could all chill out, then we might have a better time. But again, I understand that that's a really, like, that's a really weird thing to hear from the person that is giving you the stuff that's not helping you chill out. So I'm giving you assignments, and I'm going to put you through an exam and stuff like that, while saying, hey, don't worry about it, it's not too bad. So I understand that that's a bit of a contradiction and a bit of hypocrisy. So what I'm hoping is that people take enough pressure from this situation to get something out of it. But if you can't, like, if there's too much stuff going on, I mean, like, look, we've got 700 people in the course, which means that the odds of this course being completely unaffected by COVID-19 is basically nil. So someone out there is potentially going to have to go to hospital sometime before this is over. Someone out there's got family who's in hospital or something like that. If you're in that kind of situation, then, like, please, like, the health of you and your family is far more important than this course. Especially I have to remind them, especially when the uni's saying, if you need to, you can write off this term. If you need to, you can say, you can even put your best in, but your best in a difficult situation still leads to failing the course. That can happen, and that's totally fine, because the uni's going to write off that failure and let you try again without any academic penalty or anything like that. So I think if you need that, just bear in mind that the safety net is bigger and stronger than it would have been in a normal term. Yeah, I'm not sure. I just sort of launched into that. I didn't necessarily plan to say stuff like that, but I think that I think it's worth us knowing that now is not the time to put a whole bunch of undue pressure on yourselves. So, I mean, like, if you're in a perfect situation, you've got great internet, and you've got a home you never left anyway, and going in for lectures and tutorials was a drag, and you wanted to just stay at home and do them all online, and you're in paradise right now, then yeah, okay, go nuts. Push as hard as you can, but I mean, I don't think that message was for you if that's the way you think. But for anyone who's having trouble at the moment, remember that you don't need to know everything in this course. When we go for a pass mark, we are literally going to examine you on 50% of the stuff in the course, so you don't need to know everything. I'm going to talk about study tips later, actually. Like, next week, when I talk about the exam, I'm going to talk a little bit about how to focus on the bits that are going to get you marks in the course without having to focus too much on trying to know everything. Anyway, let's have a look at what people are saying. Oh, Georgia was asking if the exam would take a full 24 hours. No, the only reason it's a 24-hour exam is so that no one's disadvantaged for being in a particular time zone. It's definitely not supposed to deprive you of sleep. That is definitely not the aim. Like, technically, the exam that we're giving you is roughly, it's not exactly, but it's roughly the same exam that we would have given you for 3 hours. And I think having it for 24 hours open book means that there's actually going to be much, much more of a chance that people are going to be able to complete this, because you can go back and look at lecture notes and stuff like that. But again, this is not going to be a full-on serious closed book exam like normal, so it's yeah, you've got a bit more time to work on things. But at the same time, looking at that, we actually have less than 100 people viewing the lecture right now, which means that in terms of the timing of when I want to show you things and stuff, less people are seeing this than normal. So because of the COVID-19 situation, we're actually probably not educating you as well as we normally would. So I don't mind if the exam's a little bit easier than it normally is. Okay. Someone was saying definitely the 5th, so that means that it has been publicized, and the 5th rings a bell in my memory as well. I'm not going to look at my calendar. It's in here, but I'll look it up later. A couple of people are saying it might actually be worth handing in after 3 hours, the exam, if you want to. I mean, like, if you think you're on the borderline, if you think you're not necessarily going to pass the course, then you can take some more time trying to get some extra marks. But if you want to, you can just, like, and we'll mark it and we'll give you feedback. You'll get to see which questions you passed and you didn't. SKT Miku is asking, do we need to pass the final exam to pass the course? There are hurdles in the exam. The hurdles are things that we consider to be the base competency that you must be able to do to have understood the course. One of those hurdles is going to be the use of arrays, the other is going to be the use of linked lists. They will not be super complicated use of either, but they will be testing your basic ability to understand both of them. And so you will have to pass those hurdles. So if someone's doing really, really well in this course, they've got 100% in everything, which means they're over 50% of the course already, they still have to do the exam. Because if you don't do the hurdles, then you haven't proven that you have the base competency in those things. Oh, that probably answers George's question as well, wondering about whether it's just raw marks, but we do have hurdles, so people do still need to do the exam. AA, we are not asking you to get more than 50% in every single component of the course. So 50% total and hurdles. Those are the only things that we're asking you to do. Yeah, Patrick has it right there. Pass at least an array linked list part, otherwise fail the course. Yep. Yeah, but we'll get to that. Cool. People are answering the question already in chat. Rain, yes, the slides say Term 3 2019. They are modified from Term 3 2019. I mean, when I teach the same content more than once, I do recycle things. I mean, I did modify the slides a little, but not much. And I forgot the key modification, which was the tagline here for when I was teaching this particular thing. So the upload, I will probably re-upload it after we're done now that I've edited it. Yeah, George is calling me out here. Paylong Lee is asking if there's a chance that you do it wrong by making a silly mistake. Silly mistakes probably won't lose you enough marks for you to not pass the hurdle. So if you look like you understood it, and then you put a semicolon in the wrong place or something, or you make a typo and it's a minor error, then you're unlikely to fail the hurdle in that regard. I mean, if you look like you only half understand it and you make a silly error, then there might be an issue. But the hurdles are not marked on, you don't have to get 100% in the hurdle questions. You just have to pass the hurdle questions, which is showing that you know how to, like, say for example, if I have a hurdle question which is loop through an array and, I don't know, add up all the values in the array to a total. And you're able to loop through the array and you add things up and then you accidentally return something that's a slightly different answer, we can probably see that you did most everything. And so those kinds of things will probably get you the marks. I can't say exactly because everyone's going to have a slightly different response. Jasmine Oren is asking if there are auto tests for the exam questions. Yes, there are. So the exam is going to be similar to something like a weekly test, only just bigger. So the weekly test only has 3 questions in it. The exam's going to have at least twice as many of those practical questions, and it's going to have some other questions which are kind of were you listening questions. Like, do you know the underlying ideas about this or that? Yeah. How long is a piece of string? How long is a piece of string is actually a valid programming question. It's like, how many characters are there in this string? Okay, let's not get too far off track. I should actually be lecturing. So let's launch into it. Oh, actually, there's some other questions there. Exams will be human marked. Some of the exams will be human marked. We have an auto marking system, same as the assignments, and if you get 100% in the auto marking system, then we're not going to human mark it. So if you've already shown that you can get the code to work functionally, then we're not going to bother looking at it that closely. Also, considering this thing is a pass-fail thing, we're not going to be looking that closely at things beyond the hurdles, but we are definitely going to be scrutinizing the hurdle questions very closely to make sure that we don't accidentally fail someone or anything weird like that. Actually, it's really just so we don't accidentally fail someone. Yes, the questions will be available online. They're probably not just going to be on WebCMS. We're going to have some other system to make them work for you. But, you know, we'll do that, and Tom is working on a bunch of this stuff already in the background. The entire exam is which one of these is Mark's cat. So all the theory questions are whether you can identify chicken against other dark brown colored domestic short hair cats. That would actually be really hard, by the way. Okay, let's get into this. Okay, so yesterday we did a recap of projects with multiple files. We actually did a little recap on linked lists as well. And then we started looking at abstract data types. So the idea is we can hide the implementation of something, but provide certain functionality through the function prototypes that are in the header file. We looked at typedef and how typedef is something that allows, for example, a struct pointer and a new name to be equivalent to each other so that we can use them differently in different files. This is very much something that helps humans to understand that they're looking at an abstract object and not a real pointer to something. Because if you start thinking of it like a real pointer to something, you start looking at trying to get into the fields on the other side of the pointer, the fields inside the struct. But if you don't know anything about them, you shouldn't be touching them. So it's like me saying, oh, I can just go open the hood of my car and start pulling out parts of my engine and changing them. I'm sure there are people out there who are well versed in doing that, but I am not, and I should definitely not be doing that. Whereas what I should be doing is sitting in the driver's seat and using the functionality that has been provided for me that keeps me safe. So there's nothing in my steering wheel that allows me to turn the wheels so far that the wheels break themselves off where they're attached to the car or something like that. Whereas if I was to be able to get into the engine and do stuff, maybe I could make something like that break. So the ADT is something that allows us to use something properly and provides the functionality we need while hiding away how it actually works and the details behind it so that we don't necessarily have the capability to break it or do anything weird or wrong with it. So we looked at an example, which is the queue, and today we are going to finish the queue. So we hadn't completely done, we hadn't completely finished everything in terms of freeing memory and things like that. And I also wanted a function that was going to return the number of items, because I'll show you an example. If I try to remove something from a queue that's already empty, then I cause a problem, and there's no way for me to know whether the queue is empty or not without keeping track of it. So let's set up the queue in such a way that it will tell us whether it has items in it or not, and that might help us to know whether we can actually take something off the queue. We're also going to look at another abstract data type called stacks. Stacks are a different way of storing information, a little bit similarly to a a little bit similarly to a queue, but a little bit different. And we're going to look at the idea of different implementations there. I don't know how deep we're going to get into implementing stacks. I think I'm just going to talk about them. We might let it bleed into next week, but I'm not sure. Next week I might want to just do revision and exam talk, because I think that's quite valuable. Like, the last thing I want to do is have something like the format of the exam throw someone off. I want the exam to just purely be testing your skill, not testing your ability to sit an exam, which is a different thing. It's not what I'm testing. Testing your ability to do COMP1511. Someone heard a kid crying. Yeah, I heard that too. That was actually outside the window, so someone must have been going past outside. Yeah. Alright. So, I kind of don't need this slide, actually. I've talked already about a recap of abstract data types, but in case, functionality is declared in the header file but implemented in the C file. The header tells us what our functions are, what the inputs and outputs are, and usually has some comments to tell us what's going on in them, but there's no implementation in the header. Implementation's all in the C file. Okay, so we haven't cleaned our memory in the queue yet, so we want a function that's going to free up the whole queue. And we also want a function that returns how many items in the queue, so that makes it easier for us to know whether we can remove things from the queue. Because basically we want to know there's something in the queue before we remove it. So, back to our header file, a few things we haven't done yet. QFree and QSize. So we're going to look at them now. QFree is something like this. So we could loop through the list and free each node as we're going. We did a function very similar to this in the Battle Royale, where we looped through and we said maintain a pointer to the current node while you move the head along. After you've moved the head along, you free that current one. So let's go across here to VLab. Let me just get my cursor back. Ooh. Looking a bit slow. This was fine a second ago. Oh, maybe it's because I wasn't uploading my stream at the same time. Jeremy, the queue was first in, first out. So the queue was, we put whichever thing went in first comes out first. The stack is actually a last in, first out, which is the opposite. Okay, let me go into my queue directory. So I've got these in separate directories now, because multi-file projects prefer to be in their own directories most of the time, because when you have files called main.c, they don't differentiate themselves from separate programs, so I like to organize them. I'll open all of my files. There's a bit of lag there. Maybe I should lower the bitrate of my stream. However, the stream is already running, so it's going to be doing that. Okay, so here's the main file that we were using. It puts 3 people in the queue, it removes 3 people from the queue, and it just says which ones they are. So we saw that running yesterday, and we saw that this was working to a certain extent. My queue.h here has the functions that I'm intending to implement. We can see here QFree is something that I haven't implemented yet, so let's do that one now. Alright, I'm going to put that in here because one thing I like to do just for human readability and organization is to keep my functions in the same order in the C file that they are in the H file. It's not necessary, because as I was saying before, the C file is just going to compile things into a big pile of code instructions, and you can just jump in wherever your function is to run them. This is for us. So this is to make sure that when we read through, things are in the same order. It makes it just a little bit easier to find stuff. So, we're a bit laggy today. Here's my QFree function. Most of the time I copy paste from my H file to my C file to make sure that I don't have little typos in things, because I want them to be exactly the same. Okay, so if I want to free all the nodes in a queue, the first thing I'm going to need is a pointer to a queue. Hello, I'm not sure if you heard that one. Someone has come to say hello. There's your daily chicken, your daily dose of chicken. Alright, don't want to interrupt the lecture too much. Okay, so if I want to loop through a queue, the first thing I'm going to need is a pointer. So I might make a new one. And it's going to be a queue node pointer. So a new queue node pointer. And I'm going to call this current. And it's going to start off as the head. So the queue's head. I did exactly the same thing I did yesterday, where I was just like, head, and I forget that the head's obviously an element of the queue itself. I'm not sure many people are going to necessarily understand this, because I'm not sure many people are doing C++, but this is definitely a throwback to the way that I would work in C++, is I forget that the queue is there. And because in C++, when you're working inside certain objects, you can access the fields of the struct on its own. But let's not go too deep into that kind of thing. This is why I keep making these typos. I did say that, I think I said that about midway through the course, that like the later on we get into the course, the more C and C++ diverge, and the more likelihood I'm going to start to make typos. Because it's like I'm speaking in a native language and then trying to translate to you as I'm teaching you. This would be the same if, like, say my native language was French and I'm trying to teach in English. Every now and then there'd be a word or two I'd get caught up on. It's fine though. I can still get the code going that I think I need. Okay, so if we have the head, and I know that I'm going to be looping through the entire linked list, I can set up the structure that I want here. So the basic structural idea of looping through a list is going to be the same regardless of how we loop through the list. So this is going to guarantee I'm going to see every element in the list. And then what I can do is I can come into my linked list here and put whatever functionality I think I need in there. Oops. Oh, the lag. All right. Going to put a little comment in here to remind me where I am in my while loop. So I've probably freed all the nodes before this. Okay, so now I need to think about freeing this. So if where do I have those? Hang on a second. Maybe it's this one. Removing a node here. So what I would do if I was going to remove a node is usually I would skip it and then free it. But I think we were, where was it? Yeah, it was this one. So we had a loop pointer. The loop pointer moves along. We keep a pointer to the previous node after we've moved along. And then we free that previous node, and then the loop pointer is then going to move on to the next thing. So if you want to see this, this is last week's second lecture, is where I was looking at exactly how we were doing the freeing. So what I've got here is I'm going to maintain a pointer . So struct Q node pointer, I'm going to call that rem node. Can you actually let me just, there you go. She's just like standing next to me going, what are you doing? Okay. Where's my cursor gone? There we are. So I'm going to maintain a pointer to the node that I'm currently looking at. I'm going to say, I'm going to name that rem node for that being the node that I'm going to remove. Then I'm going to move the current onto the next so that I have access to the next pointer in the list. And I do want to have access to the next pointer in the list because I'm about to remove the rem node. So if the rem node and current were still the same, and I freed rem node, then I wouldn't be able to get the current next because I've already freed it. So I want to move the current pointer along before I free the node that I'm removing. What are you doing there? She's just sitting on my other desk. She's sitting on the miniatures that I'm painting right now. Okay, so this will then free the node that I want to remove. So this is going to go through and free the memory for all the nodes that are currently in the list. So I've got this current pointer that loops through the list until it reaches the end, and every time it moves through the list, it frees one of the nodes that as it goes past. So same kind of thing that we were doing previously. So if we want to now, we can come through to our main and say, okay, let's clean up after ourselves. So let's say, for example, I hadn't removed anyone from the list. So we've got a list with three, we've got a queue with 3 people waiting in it. And I say, actually, you know what? Ice cream store is closed. We are not giving out any more ice cream. Too bad, so sad. All of you can go home now, so we're going to free the queue. So I'm going to call QFree. Is that spelled like that? It was spelled like this. And the queue that I'm freeing is ice queue. So what this is going to do is it's going to go through and throw away the memory for all of the people that were in the queue. Let's have a look at this and compile it. Main.c and q.c. Gonna call it qdemo again. But this time I'm gonna do a memory leak check just to make sure that I'm not leaving any memory behind. There's no issues with what I'm doing with memory. So this is my leak check, and let's run qdemo and see what's happening. Okay, put 3 people in the queue, and then we finish. And the finish will be after we free the queue, and then we return 0, and it says, oh, error. Free not called for memory allocated with malloc in function qcreate in QC at line 22. QC, line 22, qcreate. Oh, I didn't clean up all of my memory. So remember, I also have a qinternals pointer, and I malloced a struct qinternals, which is one of these, that was maintaining some sort of administrative information for what was happening in the queue. I did, well, at least LeakCheck seems to think so as well, I did clean up all of the queue nodes that were created in qadd, all of these, because I didn't get an error there, but I didn't remember all of the memory that I was trying to clean up. Let me go back to my slides for a second. Yeah, so we could test for memory leaks. This is the same kind of code that I had there. And this is a reminder to all of you that every piece of memory you use malloc with, everything that you allocate has to be freed. So let's make sure that if we free the queue, we go through and we free all of the nodes in the queue. So that's fine. We're going to remove all the nodes in the queue, but we need to remember that if we have another struct that's managing the queue, that also needs to be freed. So we not only go through and free all the nodes, we also free the queue itself, which is the qinternals struct. So this capital Q, we look at our type def, capital Q is a pointer to a qinternals. So pointer to Q internals and Q interchangeable. So if I've been given a Q as input, I can use it as if it was a pointer if I'm in the place where I know the structs exist. So I can use Q to go into that struct and free it. Now I know that the struct in here also has pointers to a list, and I need to remember exactly what they are and clean them up. So I know that both of those are pointing at one linked list. There's one linked list and they're pointing at either end of it. So I've already gone, I'm going to use the head here. Q head is my current that loops through, and that has already cleaned up everything in the linked list. And after that's all clean, then I can free the memory for the Q. So when we have a hierarchy of objects, so one object governs the other objects, you've got to go from the bottom up. So you've got to clean the littlest things first in their lists, and then when you've cleaned up everything that's inside an object, then you can clean up the object itself. So now that I've made sure that I'm freeing the whole queue, let's compile that with leak check and run it again and see whether we're actually now cleaning up all of memory. Great. Leak check is no longer giving me errors. I'm cleaning up all my memory. I mean, I kind of knew I was at this point because I know that there's a struct that governs the linked list and the linked list, and then I clean them all up. So let me just... It looks a bit like this. So here's my Q internals. Q internals. And it has a head pointer that points at my Q. My Q is a linked list. Not all Qs are linked lists. You can implement a Q with an array, fine. And that's my null. I'm going to shorthand some of this stuff. And I've got a tail pointer pointing there. So this is a properly set up queue the way that I have been implementing it. And that does not say that it's a queue. The thing that says it's a queue is the H file that says this thing's going to follow certain rules. I've set mine up in a particular way. So when I'm calling free on this, what free is going to do is the first thing it's going to do is move through this list. And it's going to move through this list, freeing these nodes. It does that by starting at head and then going through. Then when it gets to the null here, it says, okay, I've cleaned up all of the nodes. Now that I've cleaned up all of the nodes, then I will clean up the queue internals. And once I've done that, you can see I've crossed off all of the blocks of memory that I've allocated for this. And then I know that my entire program has freed up all of the memory that it started using. Okay, so back to my slides. So I'm pretty happy with how that code's going to work. Those of you who have been looking at how the exam works and how the data structures are in the exam may notice that something that I'm doing here might be incredibly useful to you. I'm not going to say any more than that. I do have a habit of sometimes implementing the solutions to assignments during lectures. I'm not going to say anything more, but you know. Anyway, let's move on. So, this is our improved way of freeing all of the nodes in the queue and then freeing the structure that governs those things in the queue. So all we need to do is make sure that after we've cleaned up all the pieces that are held inside, we also clean up the thing that controls them. Okay, so the other thing that we were looking at is the number of items in the queue. It can be really handy to check how many... We've got a lot of stuff open now. Okay, it can be handy to check how many things there are in a queue for the following reasons. Okay, let's do this. And let's say I'm getting really keen and I'm going to serve everyone in the queue, and I say, okay, just serve everyone that's in the queue. If I do that, let me just compile this again. I'm going to leave leak check running because leak check's handy. I'm going to run this queue demo here, and I'm going to add people to the queue. Oh, hang on. Use after free. Oops. I've freed my queue before actually doing any operations on it. QFree should not be happening if I still have an expectation that I'm going to use the queue. Let's just run that again. Compile that again and run it. Okay. So I had these people joining the queue, these people got their ice cream, and then I attempted to remove from an empty queue, and my program ends. So I don't really want that to happen. I would like to be able to check if the queue is empty or not. And if the queue is not empty, then I will remove things from the queue. But if the queue is empty, then I will not remove anything from it. So I don't want this to be a situation where anytime the queue empties and I try to work with the queue, I end up ending the program. It's basically crashing the program because I've set it up in such a way that I can't necessarily know whether the program has finished or not, but I also I can't know if I can or can't remove something from the queue. So I'd prefer there to be something that I could check on, and that's a reason why in my queue.h I had this idea of a queue size, because if I know that the queue size is greater than 0, I'm just going to copy that because I'm going to start implementing it. If I know how many things are in the queue, I know whether I can grab something off the queue or not. So let's go into our queue. I'm going to go down to the bottom of this file and start implementing queue size. So this is going to return the number of elements that are in the queue. Linked lists don't sit at a particular size. They can grow and shrink as they please. As we've seen, we can add nodes, we can insert nodes, that kind of thing. The queue is just going to add or remove nodes from particular ends because it's got its own specific set of rules on how it's going to do things. But we still do need some way of figuring out how many elements are in the queue. So this is one way that I could do it. So I'm not even going to write this code because I'm going to show it to you and then we're going to write something different. So I could, if I wanted to, every time I call queue size, I could say how many items are in a queue. This is really simple code for how many items are in a linked list. All I'm going to do is loop through the linked list, and every time I move from one node to the next, I'm going to do a counter plus plus on this counter, and then in the end I'm going to return the number. So that's just going to literally count how many times we move in the list, and then we'll know how many elements there were. But if I have full control over a linked list, I know every time that someone has added something to the list, every time someone has removed something from the list, I can use the fact that I'm doing an ADT, and I can use the fact that no one gets access to my linked list except through my functions to count how many things are in my linked list based on counting how many times people have called the add function and the remove function. And that might be a nicer way to know my total, because my total is an actual variable that I'll keep track of. It's not something I'm going to recount every time someone asks how many things are there. So this is the trickier thing that we can do here, and again why I've got this queue internals thing. I could put the size in the queue internals, and then anytime I add or remove a node, I add one or subtract one from this number, size. So let's have a look at how we would do this. Oh, hang on. I didn't need the other slide. I was going to go across to my notes to do this. So I'm going to add an integer here to queue internals. This is going to track how big the queue is. So as I said, anytime I'm going to add something to the queue, I'm going to add 1 to the size. Anytime I remove something from the queue, I'm going to remove 1 from the size. So when I create my queue, I know that the size starts off at at 0. Because I specifically said when I create a new queue, head and tail are null, no elements in it. So size starts at 0. And then I'm going to say anytime I add an element to the queue, then the size goes up. So I just go into the queue, go to its integer size, and say, okay, there's one more element now because we've just completed an add function. And then we can have queue remove here, where we're not really going to do anything about if the list was empty, but otherwise, all of these cases here say that one node was removed. Either we removed the only element of the list, or we removed one element out of the list. Either way, the queue's size is going to go down by 1. So now, if I've made sure that when I create the queue, it starts off at 0 size, when I add an element to the queue, that number goes up by 1, and when I remove an element from the queue, that number goes down by 1, I should always know exactly how many elements are in the queue. So check out this code. Check out this super complex code for figuring out how many elements there are in the queue. That's it. I didn't have to do any work at all to figure out how many things are in the queue because I'm already tracking that. So every time I add something, I'm adding 1 to the number of things in the size. Every time I remove something, I'm minusing 1 from the number of things in the size, which means that the work to figure out how many items are in this linked list has already been done. It's already being stored in the queue size. So all I need to do if someone says, okay, how big's the queue? I just give them that number. Now, note that the person or the main file can never access queue size because it doesn't know what the struct is. But what it gets is the information through these functions. So we still need to write this function even though it's only got 1 line, because what it's doing is it's accessing a struct that the main.c cannot actually get access to. The other thing that's making this safe as well is when I return queue size, I'm giving back a value, but I'm not giving back access to the integer size. So because the main.c never has access to the integer size that's inside my queue, it can never screw up my carefully balanced pluses and minuses in there. So the size value integer that I'm keeping there is safe, but when someone asks me how big my queue is, I'll tell them the number, but I won't give them access to the variable. So that way all of my stuff in the back end is safe from accidental meddling or anything like that. But I also have this really, really simple function that just tells people how big the queue is. It might not necessarily work exactly for the assignment because this queue is simple, right? This queue is super simple, and we can definitely track every time we're adding and removing. I'm not sure, because I know that the assignment's got more complications going on, so just be careful. Be careful. I know the freeing thing is something that is really generic and can free any linked list. The size thing here may or may not work. Yeah, so Tom's saying that there could be more details there. Having said that, hopefully what I'm showing you here is useful. So, let's just test this to make sure it's working. So what I'm going to do is get rid of most of these for the moment, and I might, instead of just explicitly removing people from the list and giving them their ice cream, I'm going to do a while loop. And I'm going to say while, check my H file for the functions I have available to me. Queue size is the one I'm looking for. So while queue size of the ice queue is greater than 0, so now I'm actually safety checking this thing. While queue size is greater than 0, then I can remove someone from the queue. So I can take this, put it in here, and if I want to, I can also print out how many people are left in the queue after I do that, just by using queue size again. So I think this is what we've got here. Yeah, so I'm going to talk about how many people there are in the queue. So I'm going to say printf there are a certain number of people left in the queue. And that number is going to be queue size of the ice queue. Alright, and after we're done with that, we free, and we can return 0 at the end to see that we're finished. Okay, let's run this again and see how we go here. And so I'm going to compile that, and then run it. Creating queue for ice cream. 1, 2, 3 people join the queue. Person 1 just got their ice cream. There are 2 people left in the queue. Person 2 just got their ice cream. 1 person left in the queue. Person 3 just got their ice cream. There are 0 people left in the queue. And then it ends because we were able to check how many people were left in the queue, and we knew that. So we knew that we could not get anyone else out of the queue because there was no one else left in the queue. So we can close up shop, because we've finished serving all of our customers. So what we've got here now is a complete implementation of a very simple queue. So what we have done is implemented the idea. So the idea is a queue. The idea says that when you add something, it becomes the newest item in the queue. And when you remove something, you always remove the oldest item of the queue, and then you provide the information on it. So it's like saying you're queuing up for something. I take you out of the queue, but I'm not throwing you away immediately. I'm still going to figure out who you are and what you need out of the queue, and then serve you, and then you're removed from the queue, and the next person gets removed, etc. So the queuing up for the ice cream thing is something that makes sense. What we have done is we've separated how this thing works in this C file from what it should do, which is what's in the H file. And the main file is just there to use it and test it, but importantly, the main file doesn't know any of the internals. So it doesn't know what a queue internals is, and it doesn't know what the queue's made of. It just knows that it can use it, and it follows the rules. So we set up this kind of rules in the H, and the main can use it as it wants. You've got a bigger example of this in your assignment, of beats and notes and tracks and things like that, where your main knows that there are beats and notes and tracks, but it doesn't know anything about linked lists, and it doesn't have to. It just knows the rules for how these things fit together and says, I'm going to use things within those rules. So the ADTs become a really, really useful way of working with code, because we can guarantee that things are always going to be a certain way. But we don't know or need to care about the details of how that works. So here in the queue.c, there's particular structs and particular linked lists and things, but I could just as easily have implemented this without a linked list. Some other data structure I could have used here, and it would have been fine, so long as it implemented the functions that were in queue.h and followed the rules. So, a challenge. This queue.h and the queue and the main don't know how it's made, nor do they need to know how it's made, which means that if we wanted to use a different data structure, like an array, we could use an array to implement the queue. So that's a challenge I have for you if you want to. I mean, the other challenge is like assignment 2. You can always work on assignment 2 if you want to. But if you want some revision on arrays, can you figure out how to make a queue using arrays? Because it's different. And it's an interesting thing to do with arrays, because a queue is the kind of thing that sort of like, it's like a caterpillar. It moves through memory by adding things on one end, removing things from the other. So it's like the snake game is actually going to move around like the snake game is going to move through memory. And arrays don't. Arrays sit in memory. So how you would deal with that would be interesting. Not impossible. Not by any stretch of the means impossible. But you might have to think about how you use indexes and stuff like that to move things around. Yeah, so if you could implement Q.C using an array instead of a linked list, that would be an interesting thing to do. You may want to look at what I do in the second half of the lecture with stacks first, before we do that. Anyway, let's take a break. I wanted to say a little bit about further information about programming, things you might want to know that's more than what we know now about programming, because we're getting to the point where I will no longer be helping you with programming. I mean, obviously the first thing that you can say about like where to find further information about programming is like what courses follow up from 1511. So there's 1521, 1531, 2511, 2521. I think those are the next courses. Someone else can correct me on the course codes, because I forget what they all are. Like, I probably know more about who's teaching what than I know about the exact numbers of their course codes. So anyone who had Andrew Taylor in stream A, when we still had 2 streams in this course, he teaches one of the next courses that you might want to do later on this year. Which one's that, Tom? I can't remember. 2521? 2511? I can't remember. There's more courses. Some of them go deeper into the what we call the lower end. Oh, 2511's after 2521? There you go. Oh, 2041. That's it. Yeah, I knew there was the other one. 2041's interesting, actually. I think that one is Andrew Taylor's other course. Is it still called software construction? If I remember correctly, it's cool stuff like that. Anyway, so some of those are going to go deeper into like, what does this actually mean, memory and instructions? You know how I said there's a thinking bit and a remembering bit in a computer? You can learn a lot more about what those actually are and what your programs in C actually compile down into. We call that a lower level because it's closer to the hardware on the computer. And to a higher level, and I think it might be 1531 or 2511, where you go up to more abstract thinking about programming, where we do stuff like ADTs, but we also do things like, what if a linked list has multiple pointers pointing at multiple different things, and then we have like branching nodes and things like that. And then you can learn about tree structures and stuff like that, which is more theoretical. Like, you know, yes, we will write code to work it, but there's also a lot of thinking going on in it. So those courses, obviously, somewhere where you can go, but there's other places we can learn about programming. So you can teach yourself a lot of things, and I have some things that you could look at. So Stack Overflow, people will probably have met Stack Overflow anyway, because nearly any time you Google a programming question, one of the sites that comes up with answers is Stack Overflow. So I consider Stack Overflow to be very useful, but I also want to send you to Stack Overflow with a warning, because there's a lot of people who are answering questions on Stack Overflow who are of the mindset that there's only one answer to each question. And I think that programming is a very, very wide and sort of optional discipline, where there's lots and lots of different ways you can solve the same problem. And the way that you choose to solve the same problem is based on the situation that you're in. A lot of people prefer to think of it as there's only one way to solve every problem in programming, so they'll give you the most optimal solution in a particular situation. So just be careful with the Stack Overflow, because some of them are very specialized very specific. There's also like a whole lot of arguments on Stack Overflow. It's just like any open forum on the internet. It's just full of arguments. And there'll be people who are like wanting to optimize things to the nth degree, and they won't show you a way that's a good way to learn from. They'll just show you a way that's like, no, this is the best, right? So take everything in Stack Overflow with a pinch of salt. If you can find a way that works for you to use something that's not exactly the same as the most upvoted solution on Stack Overflow, then maybe that's the way to do it. So use it as understanding. Don't treat it as truth. It's somebody's truth, but everyone's truth is slightly different from each other because we're all in different situations looking at the code from a different perspective. If you do want to learn about other languages and things, or even C, there's a whole lot of free online courses that people do. I'm not going to list them here because there's literally thousands of them. And the other thing that I can offer is that experimentation is always going to teach you stuff. So there are always questions that I get asked, and this often happens during lectures. I mean, we may even have questions in the live chat that people have been asking, and a lot of those questions could be things like, what happens if we do this? Or what happens if the code runs like this? My answer to those questions is always going to be the same. It's always going to be, what happened when you tried that? So this is something that I was taught when I was learning painting, when I was starting out painting miniatures. Someone said, the paint can't hurt you, what are you afraid of? You can do whatever you want. You know, the worst thing that you can do is you can paint something and it looks weird and you just paint over it. My upstream is dying. I hope I'm not getting too much lag at the moment. So what I'm going to say to you is the code is unlikely to hurt you. Put it in a car, see how much it can hurt you. But the code's, like, you know, we blew up one of the VLab nodes, right, by maxing out the amount of memory it was using. We got up to 8 gigs. And the worst thing that happened was it just said, I'm just going to end your program. So I used 8 gigs of memory in like 10 seconds, and all it did was say, hey, you need to stop. So it's fine, you know, it's pretty safe. So what I want to say is, like, anytime you're unsure of what something's going to do, hop in and try. You're going to learn a lot from that. You're going to learn a lot about how compilers work. You're going to learn a lot about how programs work. This is the same as one of the things I said to you at the very beginning when we were first learning about programming, was the more that you practice something, the better you're going to get at it. Now I can give you a more nuanced response to say that the more you fiddle around with stuff and the more you find out when you run the code how it works, the more you're going to know about the computers, and the more you're going to know about the programming languages. So even to the point where you've seen all of our lab exercises and stuff like that, you could say to yourself, now I'm just going to invent a lab exercise, and I'm going to say, this is something I want to discover. How does it work if we try to do this or that? And then you can say, tests for this, and then you can go, wait up, I kind of know how to write auto tests. If I compile this against a different file with a main in it, then I could run that file with specific tests in it. So what we're trying to get you towards by showing you, like, okay, simple code with auto tests and stuff like that, and then we open this up in the second assignment to say, okay, why don't you write some of your own tests? We get to the point where you then become self-sufficient and you go, I can write any code I want to now because I've been taught how to test it. So I've been taught how to create it and how to test it and all this other kind of stuff. So I think that's really cool. I've talked through the break. So I've talked all the way through the break, so I think we'll just continue. Let's see what the questions are. Oh, I think Tom is explaining everything that's going to be in the other courses and stuff like that. Abraham, you're asking about an object-oriented course in C++. I'm pretty sure there is a C++ course at some point. I'm not sure if the stream is lagging or not, because from my end, the stream is definitely lagging. Like, I'm definitely not getting my proper amount of upstream at the moment. So, hopefully it's not too bad, what I'm showing right now. I'll just wait to see if the chat catches up, and then I'll know if people can actually hear me or not. Tom's giving a lot of course advice. We may end up taking a break so that I can figure out whether my stream is working. Because it looks like my upstream at the moment is only going at about half the bit rate that I usually get. It could just also be a midday thing. Generally okay. Lags are now and then, but it's okay. Okay, let's keep going. Because I should keep going and keep it within the time frame anyway. Okay, I want to talk about another abstract data type. Yeah, Sam, is the stream dying? Because I'm definitely not. My upstream is definitely not at the level that it's supposed to be at. So we'll see how we're going. Alright, let's take a break and I'll figure out what's going on with my internet. So just give me a sec. I'm not going to take a full 5-minute break though, but it looks like there's nothing else on my computer that's using my network at the moment, which means that my issues are unfortunately bigger than anything that I can fix right now. So we're going to have to just push on and hope that all of this is going to be recorded and you'll still get everything that you need out of this if you watch it back later. It looks like my stream is at least still uploading at least half the bitrate it needs, which means hopefully the audio is still working at least. Either that or it'll just end up being delayed for a little bit until everything gets going. Although I can see my upstream is like absolutely dying right now. We'll see how we go. It's definitely not smooth from my end. I apologize for that, but there's actually not much I can do about that because I think that's just my internet connection just not working that well right now. I guess with everyone staying home right now, everyone else is also using a fair bit of internet. So let me just check. Can people just check in now? and just say if you can hear what I'm saying right now, and I'll see what the delay is on things and whether this is working or not. Okay. Alright, that's really interesting. Okay, so you can hear me and it's working, but it's taking ages. So it's just really delayed. So I might just have to keep going, and know that you're getting what I'm saying, like maybe like 2-3 minutes after I'm saying it, because that's how bad my upstream is at the moment. So let's keep going. Still have a lecture to deliver. Still have content that I want to teach you, and if it's a little bit laggy, then we'll just live with that. Okay, so. Because you'll see the gap, you'll see this huge empty gap of me just watching chat and waiting for people to start saying things, and that's how far behind it is. It's usually only a few seconds behind, but we're like, I'd say a minute behind at least at the moment. That's okay. I'm going to keep going. So I want to talk about stacks. Stacks are similar to queues in that you put one element in or take one element out at a time, but this time, instead of it being the first in, first out, as in the first person that gets to join the queue is the first person that gets to leave the queue, this is a last in, first out. So you could think of it as something like a deck of cards or something like that, where you've got the cards and you can put a card on top, and then if you take a card off the top, it's going to be the last thing that you put there. So it's like a physical stack of things. We can't access anything underneath, but we can only access the thing that's on the top. So we can only put things on the top, and we can only remove things from the top of the stack. One of the interesting things, and this is like one of the coolest things, which is why when a program is running, it's actually got something called a call stack in it. This is actually how functions work in programs. So if I have this stack of functions going from left to right here, I have my main function. When my main function calls another function, so I'm just going to call it function 1, the way that the memory works for this is that the function 1 is then put on top of the main. Actually, it's not the way the memory works, but it's the way that the program thinks of this in an abstract way. It puts the function 1 on top of the main, and what that does is it says the main's no longer accessible. We're not running any of the stuff that's in the main. None of those instructions are running. Function 1 is running. So function 1 runs, and then function 1 calls something like function 2. So function 2 gets run there, and it gets put on top of the stack, and the only thing accessible is the top of the stack, which is function 2. So it runs. But the interesting thing is, when function 2 finishes, we would remove it from the stack. We call that popping. They call it pushing and popping to put things on or off the stack. I often call it pushing and popping for queues as well. But anyway, function 2 runs, and when it finishes, it gets removed from the stack. And then the next thing that's going to run is whatever's now on top of the stack, which just goes back to function 1. So this is exactly how our functions work, where when we call something, it then gets put on top of the stack until it returns, and then it will get pushed off the stack, and it may pass some information back down the stack to the other function that's there, and then that will run until it finishes. It gets popped off the stack into the main, and then that could get popped off until the program itself finishes. So The stack is actually something that's exactly how how we work when we're working with functions. Yeah, just checking text. Stream's very unhealthy, but we're going to have to continue. Okay, so if we were going to implement a stack, we're not going to do a full implementation of a stack today, but we'll do a little bit at least. What are some of the things that we might need in a stack? So similar to the queue, we need to be able to create it, we need to be able to free it. We're also going to be doing things like pushing and popping from the stack, which is where we add something to the top of the stack or we remove something from the top of the stack. We might also want to look at the top of the stack without removing it. So sometimes when we're working with things, we would say, okay, what's on the top of the stack at the moment? We're going to do stuff with it, but it's not ready to leave yet. So this is the same as like I'm running a function that's on top of the stack, but I haven't finished running that function yet. So I'm going to look at the top of the stack for a while until excuse me, until it's ready to pop off the stack. And again, we could look at the size of the stack. So we don't have time for all of these today, but I want to show you some of them at least. Push it, pop it, bop it. I remember that game. That was like one of those things that you'd get addicted to, and you just sit. There's a little plastic game where you had to twiddle different parts of things, and it would sing you a song and say which things you had to press. Anyway, it was fun. Okay, so here we are, and I'm going to close everything that I had here for the queue and have a look at the stack. So here's one that I prepared earlier. Strangely enough, my VLab is just as laggy as my stream. So these are the files that I made available to you already once my VLab catches up with me. And I'm going to edit these. I just thought I'd do something. If I turn off the wireless on my phone, maybe there's a tiny bit less Wi-Fi being used, although my phone's not doing anything, so I'm not sure why that would be causing a problem. Okay, I have some demo code here about putting cards on and off a deck. You can see that it's reasonably similar to how we're doing things with the queue. But more importantly, we want to look at stack.h. And the stack.h here is going to look eerily familiar to what our queue.h had, because the way that we're going to use something like a stack or a queue is actually very similar to how we would do something with a queue, except adding and removing items are specifically only going to work with the top of the stack. They're not necessarily going to work with either end of the queue that we were doing it before. So the rules are different, but the way these functions look here is actually going to look really similar. So it's like the interface is similar, but what happens underneath these functions is slightly different. So if we were going to implement this, what could our internal structure be? We could definitely use a linked list again. A linked list would be very, very easy to work for a stack. Is you could just always work with the head if you want. So you could always insert as the head and then remove as the head, or you could always insert as the tail and remove as the tail. Both of those ways will work as a stack. We could use an array. Whatever we use for this, it doesn't matter to the H file. So the H file is not going to care the difference between whether it's an array or a linked list. All it's going to care about is whether it's going to add and remove from the same end of this data structure no matter what. So let's try an array, just to show you that I can implement a similar data structure, a similar abstract data type with a different underlying data structure. So I can keep our data in a big array, a big possible size array with a large maximum size, and I can just sort of grow and shrink my stack within that. And then I can keep track of where the top is by using an index to say, okay, this is the current top of the stack. And so I can say, if I've got a certain number of elements in there, then I've got a certain index saying that's the top of the stack. So if I was going to do an array implementation, I can have all these unused cells here, so I can have a really, really big possible size for my stack, and the top is an index. So the top signifies where the data ends in my stack, and so these are the elements that have been put in the stack. The other nice thing about the top now is the top happens to also, because it's an array index, especially if I use the array index just past the number of items in here, this will also tell me exactly how many elements there are in the stack. So let's start making this. So I have a struct here, which is a stack internals. So I'm using the same kind of naming scheme that I did previously for the queue. I'm going to create a stack.c file, and the stack.c file is going to be the implementation of, this is pretty slow, alright, no, implementation of a stack, lecture, demo, oops, it's in the future. Okay, so one of the first things that I'm going to need is to include my own stack.h, so I know that I'm working with the other part of the ADT that I've got there. I'm pretty sure that I'm going to be doing some memory allocation, so I'm going to include the standard library. Cool, okay, so I'm going to have a stack internals because I have said that if someone wants to use this stack, we've got a type def here. So stack internals pointer is something that points at something that's in my C file, but I won't know what that is from my H file. From my H file, I only think of the capital S stack, and that's the thing that I'm going to use. However, in my C file, I'm going to need to say what this stack internals is. So here's my struct. Stack internals. My typing is coming up like just like a quarter of a second after I press the keys, so I'm just sort of flying blind here. Okay, so I said my stack internals is going to be just a large sized array of some kind. And if I'm going to have an arbitrarily large array, I probably want to define the max size. Max stack, extreme max stack. I'm going to keep it small for the moment because I know that this is an example program. It's not going to be very big. Don't be afraid of making this much larger if you think your program could get much bigger. That is up to you to decide how big your hash defines are. One of the most dangerous things we can do is to make this too small. Doing this would be very, very dangerous. It's really easy for me to get too big for this, but for a lecture demo, 100 is probably going to be okay. If you're doing this in assignment, I would definitely make it bigger than that in case we test something bigger. Although I don't think we've got any assignments left now where we're doing that. I mean, often in lab exercises and stuff, if we have a size of something, we'll tell you when we're not going to give you something beyond a certain size. Okay, so we're going to have the stack itself, and the stack is going to contain integers, so we're just keeping it simple. And we're going to call that the stack. Ew. This is very slow. There we go. There's my possible array. And I'm going to have an index, which is the top of the array at the moment, the top of the stack at the moment. So we're going to start at 0, and we're going to we're just have an array, and we're going to tip it on its side. So 0 is at the bottom, and then we're going to count upwards. So this gives us a structure that we can now, if we need to. Note that I don't actually need more structure than this, because when I was doing linked list, I needed a pointer to another structure, and I need the nodes and stuff like that. But since I'm working with an array, it's just an array. So it's in here as an array, and there's nothing else that I need to think about for that. So this thing is actually containing all of the memory that the stack is going to live in. Okay, so if I want to create a stack, all I need to do is memory allocate all the space I need for the stack, which is going to be the size of the stack internals, which might be the big array's worth of memory. And then I need to set the top of my stack somewhere. So if I was saying that the top of my stack was an index into the stack and was also how many elements are currently in the stack, then it would start off at 0. So I'm going to copy this stack create. Paste that there. Apologize for my internet. Although there's not much I can really do about my internet. I think I just deleted the closing bracket. Alright, here we go. Okay, so if I'm going to create a stack, I am going to have a pointer to a stack internals. Let me call that new stack. And that's going to be equal to a memory allocation. The actual amount of memory that I need, I'm going to use size of to tell me how big a data type is, and I'm going to use the stack internals structure because it is a stack internals pointer. Oops. It's a struct stack internals. Okay, so that's going to give me a pointer to a new stack, and I'm going to have enough memory that I need for that stack. So I don't need to put anything in the stack itself because I don't have any information about what's going in the stack yet. But what I do need is the information to say that this stack currently has no elements in it, and the top of the stack is currently the very first element. So where I would place a new element in the stack is at index 0. So new stack top is equal to 0. And then because someone in creating this has asked for it, where's my cursor gone? Has asked for it, I'm going to return it. Again, this is making use of the type def. So the type def in here says that the struct stack internals pointer, so this, the struct stack internals pointer is the same. We can consider it equivalent to the capital S stack. So if I have a function that's going to return a capital S stack, then I can return a stack internals pointer. So this is going to create the stack itself. Alright, just going to go back to my slides. So if I want to be able to work with this stack, I want to... a couple of questions here. William's asking that he thought stack was already type def to being a pointer to stack internals. Yes. So you could, if you want to, just use capital S stack in the code. The way that I like to do it is I will use the pointer in the C file, and then I will use the capital in the main file and the H file. So the reason I use the pointer in one place and the capital, the abstract data type in the other places, is a way for me as a human to actually remember when it's abstract and when it's not abstract. So when it's in the C file, it's not an abstract there, it's a real thing. So it's a real pointer pointing at a real struct. When it's in the H file and when it's in the main, it's not. It's an abstract idea that happens to also be a pointer, but I can't access the pointer, so I won't use it as such. So what I will do most of the time is I will use the explicit name for it in this C file. This is not necessarily the case. If you want to, you can use the capital S everywhere through the C file and stuff like that if you want to. And that's fine. It will still work. I do it so that it differentiates things for me, so I know which mode I'm in when I'm programming. So it's really just a little subtle thing that I do for my own readability. You'll find that some of these things will happen. You'll change things based on how you want to do things with code style. Yeah, I'm catching up. It's usually that the chat is ahead of me, but at the moment it's the same because of the delay in the streaming. Okay, so going back here, now we want to look at the push and the pop. So the push and the pop are going to interact only with the top of the stack. The push is going to add an element after the current end of the stack. So after the elements that we're currently using, it adds a new one on the end, and then it moves the top index up. The pop is going to return the top element of the stack, so it's going to remove it, and then it's going to move the top index down by 1. So I think I've got some here. So if I had these random numbers in here and the top was 5, so I had 5 numbers, top is 5, which means it's pointing at this empty space just above it. If I'm going to push something, I'm going to give the new number, and I'm going to write it into where the top is and then move the top 1 higher. So this is me saying the top is here. I'm going to change whatever value is there because the value that was there isn't important to me. Empty space that I didn't care about. So I'm going to add this value in here and then move the top up 1. So the top remains the number of elements in the stack and also aimed at the space just after the stack finishes. Actually, let's write the code and we'll look at popping afterwards. And after that, we'll look at locking. Popping and locking, get it? Anyway, yeah. Okay. Create a new stack and return it. So I'm going to copy the function prototype for push. Here. I might just put some white space at the bottom so we can see. And I'm going to say add a new item to the top of the stack. Slight typo there, I'll fix that up once my mouse cursor comes back. To the top of the stack. Okay, so I'm relying on the structure of my stack being a specific way. So I'm relying on the index to tell me this is the next empty space at the top of the stack. In which case I can say that the stack S and the small s stack that's inside there. I mean, maybe I should have named that differently because that could potentially get really confusing. This name here. What did I name it in the No, I did name it that anyway. Let's roll with it. See how we go. Okay, so the actual array of stack there. If I change the element which is at the current top of the stack, that's going to be the same as me saying the top this empty space here. Now I'm going to change that empty space there to be the number that I've been given. So here I'm going to say you as the stack know that you've got an array, and you also know that you have a top somewhere, and I'm going to say that is now going to be equal to the item that we were given. I don't know what's going on with my internet today, but I guess this is the downside of all of us working from home, and I'm even on NBN, but obviously it's not enough. Anyway, okay, so this is me adding the item to the stack, and then I also need to move the top up by 1, so let's get the top and add 1 to it. There. And that, I think, is all that we're going to need in terms of our code. I guess the other thing we need to check is we did have a maximum stack size. So we probably don't want to just reach a point where we try to insert something into an array in an index that's outside of the array, because that will cause just a crash in the program. Or worse, depending on your compiler and your operating system, it'll allow you to write into memory you don't have access to. Most operating systems and compilers are safer than that nowadays, but some of them aren't. So what we might want to do is put this check in here to make sure that we don't push beyond the limits of our memory. So we're just going to put an if statement in here. And this is going to say if the top is currently greater than, let's think about this, if the max stack size is a certain number and I have an index into an array of that size, then I'm going to say if it's greater than or equal to the max stack size, then I know that it has gone off the end of the array. Array holding the stack items is full. I'm going to check what error message that I was saying before. Yeah, okay, I can do that. So we'll do a printf here. And I'm going to say maximum stack size reached, cannot push. And now that I'm using printf, I know that I'm going to need my standard input-output library. This is why a lot of the time when we write programs, we just include the standard input-output library and the standard library by default, because it's very, very rare that we're not going to use both of these. Alright, there's my standard input-output library. And here I had an error here, and so to say that, like, I can't put that item on the stack, so I'm just going to have to exit. Okay, so that is going to allow me to add an item to the stack, and it's going to follow this kind of idea. Assuming that the top is pointing at the first empty element, then we're going to fill it and then move it up to the next empty element. This is going to work even if the list is empty. It's going to work up until we reach the end of the list. So this way, every time we add something to our list, our top index moves up one, and then we add one there and it moves up one. We add one and it moves up one. So it's going to keep track of where the top of the list is, and top of the stack is, and it's going to make sure that every time we add something, it goes into the next empty space that's there. So the push code's there. Now pop is going to do the opposite. So if the top is here, what we're going to do if we're going to take the top off the stack is we're going to move the top index back down one so that it is now aiming at the element that's sitting at the top of the stack, and then we're going to read that element off the end of the stack, and we're going to say this space here is now considered empty. The interesting thing about this is this space here is still holding 8. We're not actually going to delete the number. We don't need to delete the number, because us moving the top down one is the idea that that number is no longer important to us. So all of these orange spaces have some information in them. They're memory. So either they're full of zeros, if we're lucky, or they're full of just random numbers, whatever was in that memory before I declared an array was using that space. So there could be a whole bunch of random numbers in here, and including this one here now has a random number in it which you don't care about, which is an 8. We have read that 8 out, but then we've said now the top is here, which means the only valid numbers are these 4. If I add another element to the stack here, we would simply overwrite whatever was there, which at this point happens to be an 8, but we don't care because we've already removed that 8 from the idea of the stack. So our pop is interesting in that it is actually, if we just pop everything off the stack, the array will still have exactly the numbers that were in it before. But because the top index says, no, I'm below those, it doesn't matter anymore. Those numbers are not important to me, even if they still exist in the array. So there's an interesting thing about the implementation, is that I'm just leaving old data in there, but the top index is saying doesn't matter, because everything beyond me is considered empty space, even if there's something in it. Okay, that's just a bit of a subtlety there. So the pop code, similar stuff. It's going to check if the stack is empty. If the stack's empty, it can't pop. Otherwise, it's going to move the top down one, and then it's going to return whatever value it reads there. So let's go across here, grab my stack of pop, I'm going to say this thing is going to return the current top element of the stack, then remove it. So interesting when I say remove it, because it's not really removing it, but by moving the index around, it's going to make it like it didn't exist. People are, I don't know, people talking about memory allocation stuff. Yes, memory allocation needs a variable, not a pointer. Oh, so that was the actual question earlier. I don't think I answered that question, but it's a good thing that it was answered in chat. Okay, so the first thing I was going to do is check if there was nothing available to pop from the stack. So that is only going to be if there are no elements in it. But for safety's sake, in case something goes wrong, I'm still going to check for a range. I could say if top is equal to 0. But I'm going to say if top is less than or equal to 0, just in case something goes wrong and top gets shifted down into a negative number. No elements in stack. I'll do another printf here. Oops. Just allowed me to press enter for the autocomplete. And so I put my printf in the comment by accident. Okay, printf, there are no elements to pop from the stack. Likewise, we're going to have to exit 1 here because there's nothing that we could return that would make sense anymore, so we're going to have to let that go. Okay, so the actual code that's going to do it, first it's going to move the top down one. Oops. I did that thing that I do all the time, where I don't access the one that's actually in the particular structure that's been given to us. Okay, so the stack's top, if it is less than or equal to 0, it means there's no elements. So otherwise, the stack's top moves down 1, and then we access the actual stack array at the current did it again, top, and this is the value that we are going to read to return, which is the current top of the stack, so we can return that. So that code there is going to say, I'm going to read whatever's at the top of the stack, I'm going to give it back to you, but now that I've moved the top down 1, that element ceases to exist, in a sense. Alright, that's doing this, moving the top down 1 and then reading the element. And this theoretically becomes this kind of stack afterwards. Let's, actually, before we talk about a linked list, let's at least run this. This is actually as much of the implementation as I'm going to do here because I don't have time to do more than that. But we can at least compile and run this. So dcc main.c and stack.c. And I'm going to call this stack demo. And let's find out how many typos I had. There we go. The same typo that I have all the time. I forgot to reference the actual structure when I've said top. Did I do it anywhere else? Okay, I think I'm okay. Let's compile that again. Right, now let's run stack demo. Stack demo, if I go back to my main here, you can see that it's going to push 3 cards on top of a deck. I've just put some random numbers in there, and it's going to take these off the deck. So it should be that as I place them on the deck, they should come back in reverse order that I placed them. So let's see if that works. So we put 42 on top of the deck, and then 37 on top of the deck, and then 13, and they come off in the order 13, then 37, then 42. Cool. So we're getting an inverted list of items, in a sense. And so that's how our stack works, and that's how you can see how it starts to work with arrays in here in my code. And it's really more about thinking about those diagrams than it is about the code itself, because the actual functional code here is just these little lines here. Just 2 lines in each of these functions, and the idea that the top is always going to be pointed at the first empty element just off the end of the stack itself. So we're not writing much code here, but that doesn't make it complicated. So this is one of the interesting things about coding sometimes, is sometimes you're writing very little code, but it's really built up around a bigger idea of how things work. Okay, so before we finish up, questions there? Yeah, Georgia saw it. Yeah, that's a mistake that I will keep making. I love this because this particular example of the queues and stacks, I did it 3 times last year. This is my 4th time in a row teaching this. And I teach the same thing, queues and stacks, because they're very fundamental and important. But that doesn't stop me making the same mistake all the time. Stack Overflow makes sense. Okay, now the term Stack Overflow makes sense to you, going off the end of the stack by accident. That's how this works, yeah. So Stack Overflow used to be a thing that would definitely happen a lot. Pellingley's asking, may I ask what is the data structure of a stack? I'm not sure I get the stack internal setup. So at the moment we're using arrays as the data structure underneath the stack. The abstract data type of the stack says it's like a stack of physical objects. You can put something on top, but you can only access the thing on top. If you tried to grab something from in between, it would all fall over. So what we're saying is you only have access to the thing that's at the top of the stack. And we're using an array with an index to decide where the top of the stack is. And yes, exit1 is going to exit the entire program, whereas return is going to just return out of a function, pop that function off the call stack, and then use the next function underneath. Okay, don't have much time left, so I want to talk about what the other ideas are. So the underlying data structure of the stack didn't have to be an array. I wanted to show you that just to show you the difference between doing an array or doing a linked list for the same thing. But if we wanted to, so I did a linked list for the queue and an array for the stack. I could have swapped them around. Doesn't matter so long as I follow the rules in the abstract data type. So if I was going to implement these functions in the linked list, I could do something like this, where the top is actually the head of the list and all of the other objects in the list are linked lists. And I do have some code here where we could say stack internals has a top pointer, and then we have nodes just like a normal linked list. Stack create, normal empty linked list creation, very similar to the queue at the moment. If I wanted to push and pop with a linked list, the push would add the element to the top of the list, which is like inserting an element at the head of the list. We've seen code for this already, so I don't even need to implement this. You could go back and look at the insertion code we had and how to insert an element on the head of a list. In fact, this was the way that we built a list at the very beginning when we were building lists in really simple ways. Pop is going to remove the top element of the list, which is very similar to any other kind of removal of the list. I'm pretty sure that our queue was removing the first element of the list anyway, right? So this pop would be the same as the queue's pop. So it goes like this. To push, we would add a node to the top of the list, where what we would do is we'd say where the top is now, we're going to make a new object. New object is going to point at what the top used to point at, and top's going to point at it. So that's just the way that we would do that with a linked list. And here's some code. I'm not going to go through the code because we're running out of time anyway. And pop is going to do the same thing where we would remove the head of the list and then move the top of the list down one. And so our push and pop for a stack could work with a linked list, or it could work with an array the way we implemented it. The person using it or the program using it, like the main.c, won't know the difference because it's going through the interface of the H file and it's saying, given the functions that I can see in the H file, then some of these things I expect to work in a certain way, other things I expect to work in a different way, but I'm just going to follow those functions, not knowing whether it was a linked list or an array underneath. And that's the nice thing about the abstract data type. It abstracts away all those details so you don't have to think about them too much. Okay, got some code for popping there. And this is what I'm getting down to here with the abstract data types is neither of these implementations changes the header. You're not really allowed to change the header because the header is the agreed upon thing, which is the design of how this thing is going to work. The main function doesn't know the difference between what's happening behind. And if we want to, or anytime we think we need to, we can actually change what's in the C file without affecting what's happening in the main file. So if I've gone through and I've done the whole thing with linked lists, and someone says, I need a new kind of functionality, and I say, oh, that will be much easier if we do it with arrays and linked lists. I could swap out my C file with one that I've created with arrays and I go, okay, here's the array one with the new function. And the other person's not even going to know that all of their other functions have changed to work with arrays because they follow the rules and I follow the rules in the H file and it all fits together. That's one of the really nice things about abstract data types. So that's where we've got to for today. We finished our queues using a linked list. We started the idea of building a stack using an array, and we've showed that a stack could have been built with a linked list, which means that the implementation in the C file could be whatever it wants. It could be wildly different from other possible implementations of that H file and still function correctly. For example, we're going to have something like 700 different possible implementations of beats and notes in people's beats.c files, but you're all going to follow the H file, which means that from the main file, if I was to run the main file on any of your assignments, I'm not going to notice the difference. Well, I might notice if you haven't completed everything, which is fine. You don't have to complete everything. But I'm not going to notice that your code is written differently. It's all going to run the same to me from the perspective of the main file, right? And that's the beauty of having these abstract data types, is that it doesn't matter how someone's building something in the back end, it's still going to work at the other end. Okay, so we are dead on one now, although it's going to be a while before the upstream catches up with me here. But I wanted to say that that is the limit of new content that we're going to teach you for COMP1511. I don't like adding new content in the week 10 lectures, because if I was to add something in the week 10 lectures, then there would be no tutorial and lab for it, so there's no way for you to kind of cement the knowledge or anything. So the week 10 lectures are going to be some information on how the exam is going to work, as well as a complete recap of all of the topics that are in COMP1511. So we're going to go through everything from the beginning. I'm going to say a few words about everything, and hopefully that that lecture or set of lectures, because I think it's going to take me more than one lecture to go through the entire course, should be the sort of launch pad for how you're going to start your study. So it'll be like, okay, this is the list of topics, and these are the things that Mark thinks is the reasonably important bits in the list of topics. So, yeah. Thanks for coming on this epic ride that we've been on together. I mean, we're not done yet. You still got your tutes and labs and next lecture, but that is the end of any new ideas I'm going to talk about in COMP1511. So we've been through a lot. I think you've come from potentially not knowing anything about programming at the beginning to now getting a glimpse of what it's like when we work professionally as programmers. And hopefully along the way you've got some programs written that you're happy with, or that you've learned something from. But anyway, I don't want to talk too much like this is like a finality or anything like that. This is just the end of new content, but we've still got next week, and we're still going to be working on things. We've still got your tutes and labs for this week and next week, which has got a whole lot of important stuff in it. This week's got a whole bunch of stuff on linked lists. As I was saying before, when I it's entirely on purpose, drop content that can be used in the assignment, that's the whole point. You're supposed to be using the content from the lectures in the assignment. The tutorials and labs for this week also have a whole lot of content, which is really useful for the assignment as well. So hopefully that stuff all helps. And good luck with all of that. Although next time I see you, the assignment won't be due yet anyway, so we'll still be able to talk about things like that. So next week we're going to have our normal lectures, but on top of that, Wednesday afternoon after the final lecture, we're going to get together for a more casual kind of get together with CSE SOC and the Women in Tech Society, and we're going to be working on just starting our revision and things like that, and just asking questions if anyone has questions about things about what to study and stuff like that. So, let's have a look at some of the questions that people have been asking here. Patrick said, would you call this an abstract data type? Patrick, you can pack up your things and go now. You're fired. I'm halving your pay, even though I don't pay you. That's how I can halve your pay. Anyway, thank you, that was funny. Paylong Lee says, the info we're storing are all integers. Yeah, for the moment, the info that I was storing in the stacks and queues were all integers. So the stack, the underlying data structure that I used was an array of integers. The queue, the underlying data structure I used, was a linked list of integers. Obviously, it's not limited to that. Obviously, if you're going to get into more detail, you could do a linked list that has a lot more information than just integers. Often when I'm doing quick lecture demos, I will keep the data structure as simple as I can. William's saying the thing's an array, which is why we have S stack, S top. as in the square brackets for array. Yeah, so when I did the stack implementation, there was an array underneath it. When I did the queue implementation, there was a linked list underneath it. I wanted to show you that it didn't have to be one or the other. So the only thing I had to adhere to was the H file. The things that I was going to care about when I was building it was whether it was an array or a linked list, and there were many different ways to build it. So for example, I have here push and pop examples if I'm using an array for a stack. But if I wanted to use a linked list for a stack, I could definitely, and I would just write different code. But from the main wouldn't know the difference. We could interchange those and it would be fine. AA is saying, aren't queues and stacks just linked lists? Queues and stacks are ideas. They are not linked lists. They are ideas of containing data so that the queue was first in, first out. So the first thing that went into the queue is the first thing that gets removed from the queue, and the stack was a last in, first out, which is the last thing that I put in the stack is the first thing that gets removed from the stack. However, neither of those things says whether they're a linked list or not. I used a linked list to build a queue, but the queue and the linked list are separate things. So the data structure of a linked list is a very low-level thing where we look at memory and pointers and stuff like that, but a queue is an idea. We can do a queue with humans in a shop, right? It's a completely different way of storing memory in a human brain or whatever, but it's very different from a linked list. But the idea of a queue, first in, first out, is still completely observed by a queue of humans in the same way that it could be observed by a linked list if we implement it in a certain way. So I want to see that distinction, that a queue is an abstract idea and a linked list is a physical implementation that can be used to work with that abstract idea. So Jeremy, I think, was answering that. Yes. Controlling the way that we use the linked list makes it either a queue or a stack. And William's also saying we could have implemented stacks with linked lists. Yeah, okay. This question's already been answered. Great. I'm glad AA is understanding that now, which is good. People are singing songs. Georgia, a stack of humans in a shop. In order to buy food, you have to climb on top of everyone. And if you can climb on top of everyone, then you get the food first. I feel like there's a reference to purchasing toilet paper and like the physical fights that were happening over toilet paper here. But I don't really want to go there. So that's why I used a queue for buying ice cream as my example for the queues, and for the stack I used a deck of cards, because a deck of cards can be piled on top of each other better. So we're going to move on from the idea of a stack of humans here, and I'm going to wrap it up for today. So I will talk to you next week. Next week, we're going to begin our revision for the course by going over everything. I'm also going to talk about what's in the exam and how the exam is structured. I think that'll be reasonably important. People are going to want to see that. So we're not completely finished yet. But yeah, I'll talk about that all next week. See you then.